Now this procedure that we've been using to build up electron configurations by counting across the periodic table has got a name. It's called the Aufbau principle, and Aufbau is German for building out. And it works almost all the time, but there are a couple of exceptions that I'd like you to know about. They occur at chromium and copper. And there are many other exceptions besides these two, but these two are kind of, they illustrate some of the issues that make the Aufbau principle not work as well as we'd hope it would. Okay, so if I look at chromium, it's here, and if I look at the end of the period, its core is argon. So after argon, I'm going to count up to chromium. I'm in the fourth row in the S block, so this is 4s1, 4s2. And then I have 3d1, 2, 3, 4. So this is the configuration that the Aufbau principle, the building up procedure, gives me. Now, the actual configuration looks like this. And I'm going to put it in shell order. Now what happens is that as you put electrons into the 3D subshell, its energy gets lowered. It actually does slip into shell order after you fill it. So both of this configuration actually reflects the energy level ordering that you see, and that's a 5 there, 3d5, 4s1. Why did this happen? Obviously what happened was that an electron dropped out of the S into the D. It's hard to see what's going on with just subshell notation. So let's write this as an orbital diagram. We got our 3 Ds. And our 4s. And when you have 3d5, all the Ds are spread out and lined up. And they can be lined up with the 4s. Now, you've taken those 6 electrons and you've spread them all out and lined them all up. They were as far away from each other as possible. If you'd looked at this one, you have a pair in the 4s, so there would be 2 cramped into the 4s. Now, electrons repel each other, they don't like each other. So that raises the energy of this configuration, cramming those 2 s's into the same orbital. And they can be more spread out here. They are negative, they repel each other, they can be more spread out in space here, and this actually is the lowest energy configuration. But it is not the configuration we got by counting across the table. Now, you can summarize this. You can say half filled D and F subshells have extra stability. Why? Because you're spreading the electrons out more. So chromium acts that way. 4s tips into the 3d. You'll see that molybdenum does that as well, but tungsten doesn't. All right, let's look at another exception. Copper. Copper also doesn't give us what we expect. Here's copper. Let's do its electron configuration. It's going to be argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is what I expect. But my actual configuration is for copper is this. And I'll put it in shell order again. Now what happens is that, like I mentioned, after you start to fill the 3D subshell, its energy goes down when you put electrons in it. And it becomes lower energy than the 4s by the time you put a lot of electrons into it. So these things aren't rigid here. They're not like shelves. They actually tip a little bit depending on how many electrons you put onto them. And if the 4s is higher energy than the 3D, an electron can go and tip into the 3D. Now, you can summarize this kind of behavior too. You can say completely filled D or F subshells have special stability. Now, you're going to see this with some other exceptions. It's not just copper that does this. Silver does it as well, and I'm asking you about silver below. Silver's got a krypton core, you're filling up 5s2 and 4ds, but otherwise it's going to look like copper. The actual silver configuration is going to be 5s1, 4d10, and gold does the same thing. So the elements that are underneath copper act the same way as copper does. So here are two exceptions. I'd like you to know both of these. This is the actual configuration that you have here. And how often should you worry about this? How many exceptions are there? Well, I've got them colored in on the picture that I'm showing you above this video. You can see I've got some colored in red. Those all don't act the way you would expect. The ones in the beginning of the lanthanides and the actinides, the d orbitals and the f orbitals are very close in energy, and they tip back and forth between filling d's and f's for those elements that are colored in red in the lanthanides and actinides. And there are some other ones that have configurations that you wouldn't predict from the Aufbau, and they're in red. In the actinides, I have gadolinium marked, and that's got a half-filled F subshell, so you can kind of explain gadolinium the same way we explained chromium here. You've got a half-filled subshell. And the same thing with curium, Cm. But I wouldn't worry about these. Here's the approach that I would take. The Aufbau principle isn't 100% reliable with occupied D and F subshells. So if it really mattered to me, I'm going to get, the Aufbau principle is going to give me a configuration that is approximately correct. But if it really mattered to me, I wanted to be 100% correct, I would always double check my configuration. If it contained D and Fs, I'd go and look up the actual configuration and see if I was hitting an exception.